Hi folks, so welcome back to lesson number 32, and this will be about charge and electric fields. Now we've already covered some of these concepts in class before Christmas, so some of it will be revision hopefully, but there is a lot of new material in here as well, so please take the time to go through this and make sure you understand it. So we're going to look at describing the electric field around charges in parallel plates, define the volt, carry out calculations involving volts and the speed of a charged particle, and I would say that this is probably the most important learning outcome, so if you don't understand the rest, make sure you definitely understand this one here. And then finally, define the electron volt, which will come in really handy when we start looking at quantum theory and particle accelerators as well. So first of all, what are electric charges and fields? Well, in electrostatics, there are two types of charges. So electrostatics is a study of non-moving charges. Remember, static means it's not changing, and electro to tell you that we're talking about electric charges. They interact with each other via electric field lines, and in this case, positive charges, the field lines always go out the way, and negative charges always go in the way. And we're going to revisit this quite a lot later on when we look at particle accelerators. Field lines always have the direction shown for electric charges and travel the shortest straight line path. Because they have to travel in the shortest path, sometimes that straight line path might become curved, as you remember from previously. They never cross each other, because if they did, that means, for example, this positive charge, if this field line crossed over here like this, it means that that positive charge is interacting with itself, which it can't do. And the closer and more field lines, the stronger the field. So to represent a stronger field, what we would do is we would draw more field lines around that charge, and those field lines would also be a lot closer, like I'm doing just now. And obviously, you always have the direction of those field lines as well. And by the opposite argument, the fewer field lines there are, the less or the weaker that field is. Okay, so if you put two different charges together, this is the type of diagram that you'll get. Notice how if you've got a positive and negative charge, these field lines will now point to what these two charges will do, which is in this case, the positive and negative charge would be attracted to each other. Because remember, positive charges, the field line goes out the way. Negative charges, the field lines go in the way. So they kind of match up, if you like. If we have two positive charges, however, notice how because they both point out the way and they can't cross each other, they start bending away from each other in that curved way. And this tells you that these two charges will repel each other, which is what we know by experiment. So you can see why these field lines can't cross each other. Okay. What other field lines have you come across? Well, you can probably think straight away the most common one is magnetic field lines, which would have a very similar diagram because instead of having positive and negative, you could have a north and a south. Not so obvious would be a gravitational field strength, or field line, sorry, because gravity also has field lines that represent how strong it is. But in the case of gravity, you don't get positive and negative gravity, you only just have mass. Okay, so let's look at gravitational field lines in a bit more detail because gravitational field lines are a lot easier to understand and more intuitive. So supposing there is a gravitational field, and let's just say the gravitation is pointing down the way because the ground is at the bottom of my page here. Now, if we have a ball in that gravitational field and the ball's been lifted up a certain height, what energy does the ball have? Hopefully you all know it's a potential energy. And in fact, at higher, we'd probably expect you to be able to tell me that the potential energy, if I gave you the mass and the height, you can calculate it as mgh. Okay, so feel free to do that just now. I'll put that in just to give you some numbers to make this a bit more obvious to kind of try and understand it. Now, let's just suppose, by argument's sake, we move this ball along in this direction. So what we've done is we've made the ball move perpendicular to the gravitational field, and also we've not changed the mass or the height of that ball. So if we were to calculate the potential energy, what could you say about the potential energy of the ball at point 1 over here and point 2? Hopefully you'll be able to tell me that the energy of that ball, the gravitational potential energy in this case, is exactly the same. So it's a bit of a strange idea because we know we've actually done some work to move it along the field, rather across it, not along it, but we haven't actually changed its energy. And so because of this special situation, we give it a special name. We actually call this equipotential lines. So equipotential lines represent a position where the energy is the same. So for example, this would be an equipotential line. This would be an equipotential line if the ball started here and then it moved further along, say to here. This would be another equipotential line, again, say if the ball started here and moved along here. And what do you notice about these equipotential lines? Well, first of all, hopefully you notice that they are always perpendicular to the field lines themselves. So you can see here, I'm always moving across it. And secondly, you can probably notice that they don't move along the field lines, right? And that's the really key idea here. So looking at more complicated diagrams, you can see that you can get slightly more interesting equipotential lines. So for example, if we've got two electric charges, so we're now bringing this back into electric fields here. And can you see here how the equipotential lines tend to curve depending on the shape of the field lines themselves? So to summarize what we've done, equipotentials are always perpendicular to field lines. Moving along an equipotential requires no net work against the field. Now, when I say along, I mean we're moving along the equipotential lines and not the field lines. So to focus now more on electric fields, because we are talking about electric fields here, let's look at a situation where you've got two metal plates, one which is negatively charged, called the cathode, and one which is positively charged, which is called the anode. Now, an electric field between two parallel plates will give us a uniform field, and this is what a uniform field looks like. Notice how the field lines are all parallel to each other. Notice as well how the spaces between them are all even as well. And notice again, I've got my field line directions going from positive to negative. So quite a lot of information there for you to take in. Try and recap that. I've moved to my laser pointer to kind of make it a bit more obvious what I'm pointing to. Now, what's important of a uniform field? It means that the electric field applies a constant force. And that's really important because when we did Newton's second law, we always assumed that the force was constant. That meant the size, the magnitude of the force, always stayed the same. And that makes our situations and our physics a lot more easier to figure out. So to show that the force is constant and the electric field is uniform, the lines that are representing the field are evenly spaced. Okay, so a few more bits of physics here. Charged particles always move along the field lines, i.e. parallel to the field lines, as you can see in my wee animation there. And remember our old rule, opposite attracts, like charges will repel. So for example, positive will always go to the cathode, negative will always go to the anode. What happens to a charge that enters at right angles to the field lines? Well, this is where it gets a wee bit interesting because we have to remember that the charge will be attracted or repelled to whichever plate that has the opposite or like signs. So in this case, if we have a negative charge going along the way, it will do the following. And you can see, although the animation at the end is a wee bit wrong, so I'll draw it, it takes a sort of a curved path. So it takes a path which goes a bit like a projectile. Okay, so we could actually use this in quite a lot of things, but I'm not going to go any more into that just now. So how does our knowledge of equipotential applies to electric fields? Well, for a uniform field, it's nice and straightforward. It's just like the gravitational situation. Equipotentials are perpendicular to a field line. So here you can see my dashed lines are the equipotentials. So this is one equipotential, 2, 3, 4, 5, and you could have lots and lots of these. I've only drawn a few so we can talk about one or two things. The energy of a charge along the equipotential is the same. So remember what that means is if I have a charge here, and if I move that charge to over here, then the energy on that charge would still be the same. Similarly, if I had a charge here, and I moved it this way here, because it's still set on the same equipotential line, the energy of that charge is still the same. So there's nothing new there. We've really just applied what we talked about for the gravitational field to an electric field. Now, you might remember voltage is called potential difference. So where did this come from? So let's try and delve into the physics a little bit more. So first of all, to move from one equipotential to another takes energy, or the technical term is work is done. And in particular, we're saying that work is done against the electric field. So in the situation in my diagram, we have that the particle, the charge, is moving from this equipotential down to a second equipotential. Now notice in this case, the charge is moving parallel to the field lines, so we know that work is done. It's no longer moving along the field lines, or rather along the equipotential lines, which is why the potential of the charge is changing. So the work done, or the difference in energy, is given by the difference between the two potentials moved by the charge. So whatever the energy or the potential, is here, and the potential is here, the work done will be the difference between these two. Don't worry if that's a bit confusing, because I'm going to show you a numerical example later on. And because it's the difference between the potentials, we call it a potential difference. So let's do this with some numbers to try and consolidate this idea. So first of all, to move from one equipotential to another takes energy or work done. So let's say, for argument's sake, at A, there's a potential of 100 joules, and at B, there's another potential at 400 joules. And this is just for argument's sake. So if the initial potential was 100 joules, and the final potential was 400 joules, then the potential difference, remember to get a difference in physics, it's always final minus initial. So 400 minus 100 would give us 300 joules. So in summary, each charge needs 300 joules to move from potential A to B. That's assuming it was a negative charge. So can you see now where this idea of a voltmeter measuring potential difference comes from? And also how we talk about the voltage splitting across a voltage divider. Okay, here's another analogy which a friend actually told me, which is, imagine you're on the Eiffel Tower, and imagine that each height of the Eiffel Tower is like an equipotential. So if you were here on the Eiffel Tower, you could move across it and you wouldn't really change your potential energy or your energy. Similarly, if you were down here, you could move along it and you wouldn't really change your energy. Now, the difference between the equipotential gives us the energy. So it's a difference from here to here, or from here to here, that gives you the equipotential. So the idea is, the higher you jump from the Eiffel Tower, the greater the difference between the grounds, the more energy you have. So the bigger the difference, the more energy you have. Now, if you don't believe me, you can do this at home. Try and say, touch a spot on your wall without moving. Try and touch a higher spot on your wall. You might have to jump. And because you're having to jump, you need more energy because you're trying to reach a bigger height. So therefore, your potential difference, if you like, is more. So all of that is just the concepts, it's the idea. How can we put this into an equation or a relationship? Because remember, these relationships and equations kind of define all the physics. So to move a charge in an electric field, work must be done against the field. And that's the technical way of describing that. So get used to this kind of phrase, work must be done against the field. The work done is given by a very simple equation. Work, or EW, so there's two notations that you could use, is equal to QV, where Q is the charge in coulombs. Remember, that's got units of capital C, and V is the potential difference in volts. So if you had to work out the work done to move a charge in a field, you would multiply whatever the charge is times the voltage, or the potential difference. You can think of this as being similar to potential energy from work done against a gravitational field, except in this case, the equation is EP is equal to mgh. So before we look at the equations, let's tie up the idea of potential difference with our equation, just like we did with the conceptual part of the lesson. So here's our equation. And remember, we can rewrite this for voltage to give us a definition. And remember that technique, dimensional analysis that I showed you before. Instead of plugging in numbers, if we plug in units instead, then this would give us, well, work, remember, is an energy, so it's got units of joules. And that would be per. And remember, Q is the charge in coulombs, so it's joules per coulomb. So this allows us to find voltage as the energy per unit charge. And if you remember when we did internal resistance, what was the definition of EMF? It was the number of joules each charge picked up as it went through a battery or a supply voltage. So hopefully you can now see us tying together some of the concepts. Okay, so let's try and look at what this actually leads to. So first of all, if we've got a positive charge moves in the electric field, it must have a kinetic energy. So if you can see here, the kinetic energy comes from the work done by the field or against the field. And so that means the work done must be converted to kinetic energy, conservation of energy. So QV is equal to half mv squared. And you might remember this because I did this before the Christmas holidays. And if there's one thing that I really want you to take away from this is this idea that EW is equal to EK, QV is equal to half mv squared. This means we can now calculate the velocity of the charge in electric fields if we know the mass of the particle and if we know its charge and the potential difference applied to it. And we can use this in a whole range of applications. So again, you can think of this as being similar to EP is equal to EK, where instead of moving in an electric field, it's a ball being lifted up in a gravitational field. And if we drop that ball, that potential energy is converted to kinetic energy. So let's look at some calculations and see how we use this equation. Now, one of the things I like about this particular topic is that it really works with the MTV technique. So remember my MTV technique of KFC, know it, find it, calculate it. So even before we read the question, we can try this. Let's just write down what we've got from the question. So first of all, we've got a pair of plates as a potential difference of 4,500 volts. A proton is placed on the positive plate. The charge of the proton is 1.6 times 10 to the negative 19 coulombs. Its mass is 1.67 times 10 to the minus 27 kilograms. So let's just write down using our KFC technique. Know it. So let's write down what we know. So first of all, V or PD, if you want to be a bit more exact, is 4,500 volts. So that's nice and straightforward. Okay, we know the charge of the proton, so Q, and I'm going to put a wee subscript P to remind me that we're talking about a proton here, is equal to 1.6 times 10 to negative 19. Now, again, please be patient with me. I am writing this on my mouse pad, which is not the best thing in the world. And it might give you a bit more time to kind of write this down as well. And then finally, we've got the mass of the proton. So again, M with a small subscript p to show that's a proton is 1.67 times 10 to the 20 minus 27. And again, that is in kilograms. So nice and straightforward. Now remember, check that your quantities are in the right units. So you know you can use the equation. So first of all, calculate the energy gained by the proton. Well, the energy gained here really is a fancy way of saying what was the work done against the electric field, not gravitational field. So all we do is we say EW is equal to QV. Now, here's where the KFC techniques really comes in handy. Even if you didn't know what equation to use, I would hope you'd be able to look at what you've got and say, well, I've got a V, Q, and an M, and I want an energy. So what equation can I use that has these three quantities, or maybe two of these quantities? And you can see straight away, EW is equal to QV. I've got V, I've got Q, I plug it in and then I work it out. So I'm going to leave you to do that because it's easier for you to do the calculation and write it out. So all you do is you do 1.6 times 10 to the 19, times by 4,500. And remember, your answer is in joules. Okay, so you work out what that answer is. Part 2, the velocity of the proton as it approaches the opposite plate. So first of all, we're assuming that the proton now has kinetic energy, and that kinetic energy comes from the work done against the electric field. So in other words, the first thing we write is EW is equal to EK. Now, again, I would hope with the KFC technique, because you've got an energy here and you've got a mass there and it's moving, you'd be thinking, well, what kind of energy does it have if it's moving and it's got a mass? It's kinetic energy. And so once you've done that, you're kind of on a slightly easy streak now because it's really just mass. You sub in for your equation a half mv squared. Okay, you know what EW is from part 1. You know what the mass is because you've got it there, and it's just a case of rearranging for v squared to give you the velocity. Now, a wee top tip, if you don't like rearranging equations, what I would do is I would substitute in the numbers, work out what a half times mp is, the mass of the proton, and then try and work out v from there. If you have any problems with that, let me know and we can do a wee power up lesson on that at some later point. Okay, so let's look at another example now, and this is more tricky example because it's actually from an old past paper question. So proton beam therapy is used in some hospitals to treat certain types of brain tumours. Protons are accelerated between an anode and a cathode with a potential difference of 5 kilovolts. And there's a nice wee diagram there and 3 questions shown underneath. And first of all, it is important that you know what an anode and a cathode is. Remember, cathode is the negative part and anode is the positive part. And we're asked to do 3 things here. So let's look at how we would answer this question. So I put a wee smaller one to allow me to focus on each question. So first question it says, or you would maybe even try and do straight away our KFC technique. So you could write down potential difference as 5 kilovolts. And remember, we want voltage in volts. So kilovolts in volts is times 1,000. So that's actually 5,000 volts. We know it's a proton. So we know we probably have to look at the mass of the proton and the charge of the proton. So explain why protons released at the anode are accelerated towards the cathode, and it's 2 marks. So for me, a typical answer would be, well, the protons are positive and the anode is positive and the cathode is negative. So like charges repel, unlike charges attract. So the proton will be attracted to the negative cathode. And that would be a typical answer. 1 mark for telling me what the charges of the anode, cathode and the proton are, and 1 mark for telling me that unlike charges attract or like charges repel. So a fairly nice, straightforward question to get you into the problem here. Okay, so we're now going into the calculation because it says calculate the work done in moving the charge between the anode and cathode. So in other words, it's saying what is the work done against the electric field? And again, if we use our KFC technique, so here I would really expect to write down voltage is 5,000 volts. So notice straight away I'm actually converting my quantities into the correct units. Okay, we know it's the mass of a proton, and we know we probably need the charge of a proton. And notice how they don't tell you you need this information, you have to figure it out yourself. But it's a routine because you know whenever we do calculations with electric fields, you're always going to have to know information like the mass of the charge or the actual value of the charge itself. And these two values are given to you in your data sheet. Now, because I don't want to write everything out because it'll take me ages, I'm going to jump straight to the next part of the KFC technique. We've got know it, find it, so find the quantities here and find the equation, which hopefully you remember is EW, and that's equal to QV. Where Q is just the charge of the proton, 1.6 times 10 to the negative 19, and V is the potential difference applied to it, 5,000 volts. So all you do is you plug your numbers in, work out your answer, and just remember the units are in joules. And remember, you get 1 mark for writing down the equation, 1 mark for subbing in the values, and 1 mark for giving the correct answer with the correct units. So that's why it's a 3 marker. Okay, and it's a routine that you can always do using your KFC technique. Okay, final one is calculate the final speed of the proton at the cathode. So again, it's really saying all of that work done against the electric field has now been converted to kinetic energy. So again, if you remember from my previous worked example, what we're saying is EW is equal to EK. So we're saying that all of that potential energy from the electric field is converted into kinetic energy. So we then sub in for a half mv squared. So this is where the mass of that proton is really important. EW we've already calculated in part B, so we just put in our answer there. And remember, I would work out this bit first, and then rearrange it for V squared to make it easier to get to the velocity. And remember that V has units of meters per second. Again, I've not put the marks on this one, but this would be a standard 3 marker. 1 mark for having the equation, 1 mark for putting in the right quantities, and 1 mark for the correct answer with the correct units as well. Now, if you look through those 2 examples, I hope you can see there's a routine that's similar to both of them. You write down what you've got. You might have to find the quantities from the data sheet. If you're calculating the work done against an electric field, it's always QV. You then use that answer to work out the velocity using the equation a half mv squared. So try and be aware of what it is that you're doing to get to the answer. Because quite often in physics, getting the answer is just a routine which you can follow every time. Okay, we're now coming to the final part of the lesson. I appreciate it's almost half an hour, so feel free to have a break to come back to this. I don't expect to do this in one sitting. What is the electron volt? Well, if we take our equation EW is to QV, we can use it to define a new unit. So this new unit is called the electron volt, which is sometimes written as a small e capital V. Small e stands for electron, V stands for the volt, and it's simply defined as the amount of energy gained or lost by an electron moved across an electric potential difference of 1 volt. So that's the definition of electron volt. Please try and learn that definition. So we can get a value for the electron volt because we know the charge will be the charge of an electron because it tells it's an electron being moved. We know the voltage is 1 volt because that's in the definition. So if we plug in the numbers, we get that 1 electron volt is equal to 1 eV is equal to 1.6 times 10 to the negative 19 times 1, because this is the charge of the electron and this is the potential difference. And so 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Now, this is a really important quantity that we're going to come back to when we look at particle accelerators and atomic spectra. So I've introduced this to you just now because you may come across this in some of the literature. Now, we can develop this further because in particle accelerators, we don't normally talk about mass in terms of kilograms, because remember, these particles are a lot smaller than your protons and neutrons. So we talk about them as something called an electron volt mass. And we get this from Einstein's equation, E is equal to mc squared. And what we do is we say, well, mass is equal to energy over c squared. But the energy in this case is our electron volt. So we can sub in for EV instead of writing E, and we get EV over c squared. So this is also a unit for mass now, EV over c squared. And if we plug in numbers for these different quantities, dimensional analysis if you like, then we get that 1 electron volt over c squared is equal to 1.783 times 10 to the negative 36 kilograms. So this allows us to define the mass of really small objects. And to give you an example, you can see here, these are subatomic particles called quarks, which we're going to look at later on. And you can see that the mass is given by mega electron volts over c squared, giga electron volts over c squared, and similarly for here as well. Okay, now don't worry too much about the details of this. I don't expect to know all of this off by heart, and we're going to spend a lesson on the different parts of this as well later on. But this is just to show you where electron volts and electron volt mass will come in handy.